150 plus companies are involved in a riveting new form of transportation. Names like NASA, Airbus, and Boeing are involved. The advanced air mobility industry is expected to fully commercialize electric takeoff and landing vehicles after 2035. The development of this cutting-edge technology will allow air taxi flights, emergency services, and surveillance systems to be carried out through autonomous drones. Right now, we're seeing trends of urbanization of up to 60% by the year 2030. That's less than a decade from now. And I get it. Some of you might be questioning the legitimacy, if it's real, is it actually going to happen? Is this too ambitious of an idea? Well, whether you like it or not, the industry is on the move. For example, a key player in the advanced air mobility industry named Archer has just partnered up with Kilroy to develop a plan in San Francisco to reduce 1 to 2 hour commutes to a matter of minutes. Some of you guys may have heard of Archer. They actually had a commercial in the Super Bowl recently where they had Usher in one of their midnight eVTOLs. If you haven't, you may have heard of Figure, the robot company, competing with Tesla's robot as well, and it's founded by the same serial entrepreneur named Brett Adcock. Now, Archer has also made international strides with countries such as the United Arab Emirates, and they are investing millions of dollars into the venture, and as we speak, they're in talks to commercialize air taxi flights. Now, additionally, a company called Whisk, they're a subsidiary of Boeing. Right now, they've actually partnered up with Sugar Land in the state of Texas to develop to and from airport transportation using autonomous drones. These projects that I've just mentioned are ambitious, and the timeline for them are still within the next decade, so we could really see this become a reality relatively soon. Yeah, I've named the key players, but what exactly does the industry look like? What are the challenges involved? Are we even headed to the right track? Is this actually viable, like I've said before? Now, the advanced air mobility industry is very vast and complex. As you can see on screen right now, there's puzzle pieces that all play together to make this industry a reality. Right now in this video, we'll only be diving deep into the vehicle design, more specifically the autonomous technology that is required to make autonomous air taxis a reality. Now, mind you, in the advanced air mobility space, not all of these eVTOLs are autonomous. In fact, only a minority of companies are tackling the challenge of autonomous air taxis. All right, let's get down into eVTOLs. I've called them electric takeoff and landing vehicles. In short, eVTOLs is the name. This name will be said a lot throughout this video, and it's important to really understand what eVTOLs are before we really get into the nitty-gritty of the technology. As a starter point, let's define some terms here, and we'll be referring back to these points ever so often here throughout the video. First off, we have airfoils. These airfoils are essentially just shapes where if they are against the fluid, a lift will be generated. As you can see on screen, there's a specific shape. The fluids interact in a specific way with the composite or the shape itself, and it generates a lift from underneath. And this is important. And then we're talking about rotors. What are rotors? Now, even though they have the spinning motion, essentially they're a set of airfoils that are rotating. And if those airfoils are rotating, they're having contact with fluids in the air as we know it, which allows them to lift. Then you have propellers, right? Well, propellers, rotors, aren't they the same thing? Technically, yes, but they have two different functions. Rotors, they generate a lift, right? Whereas propellers, they generate a thrust, right? So when I say propellers, when I say rotors, they're different and they have different functions. Then we have something called a flight envelope, and the flight envelope is essentially a list of parameters and characteristics where the vehicle is aerodynamically stable. So you could say the flight envelope of a specific eVTOL would be you at this range of speed and at this range of altitude and at this range of acceleration. All of these that build up define a vehicle's flight envelope. Now, eVTOLs, they come in a variety of variations. There's four main ones here. We have the multi-rotor design, tilt-rotor design, compound design, and you have the tail-sitter design. And let's start with the multi-rotor design. Now, these eVTOLs are kind of like those stereotypical drones that you see everywhere. You have just 4 rotors and they fly up, right? As you can see on screen, this is an example of a multi-rotor eVTOL. And the great thing about this is that it has really minimal cost, and it's actually very efficient in using its structural materials. So it's very simple, and it's great for budget. However, because of these limited budget, these multi-rotor designs generally have a lower flight envelope, right? They're not able to do much things and in a precise manner, right? They're limited because of this. Now next we have the compound eVTOLs, and as you can see on screen right now, this is by Airbus, more specifically City Airbus. It's their City Airbus next gen model where they're combining propellers and rotors in their design, and this is what makes up a compound eVTOL. And if they were initially in a landing position and they want to hover, they'd use the rotors, and then if they want to transition towards forward flight, they'd use more of the propellers. Now it's not just one or the other here, they work in tandem, but it's the existence of both the propellers and the rotors that make these compound eVTOLs unique. In doing so, they have a larger flight envelope. They're able to fly faster, achieve higher altitudes. It gives them more freedom to do certain functions. Now another design is the tilt rotor eVTOLs. Now this is interesting, particularly because from an engineering standpoint, how do you design a rotor that literally rotates itself, right? And have the structural integrity to allow the eVTOL to fly, right? That's a challenge that these engineers are willing to take for specific advantages, right? Aerodynamically and efficiency as well. However, tilt rotor eVTOLs have a lower efficiency when they're hovering, right? But when they're flying forward, there's a lot more efficiency and a lot more advantages there. And we have tail sitters, and they're very unique. They look like the little sibling compared to all these other designs that we've mentioned previously. But these guys pack a punch, right? They literally sit on their tail, and when they fly, they move their entire body to angle themselves where they want to go. As you can see from the image in front of you, this is the shape generally of what tail sitters are. And the main advantage of these eVTOLs is that they can traverse very intricate paths. When you have the multi-rotor eVTOLs, for example, they might lack in this. If they're in a dense urban environment and if it's very difficult to traverse, you'd rather opt for a tail sitter eVTOL, for example. I know I talked about the excitement of air taxis and how we're actually going to be able to skip traffic, right? That's amazing. But the functions of eVTOLs don't lie just in commercial and human transport, but we could see them being used in emergency services and surveillance, like I've mentioned earlier. So tail sitters are probably going to be more dominantly used in those fields. Now, it's estimated by 2035 that these eVTOLs will become fully autonomous. And in order to reach that reality, there are 2 paths. There is the piloted path and the pilotless path. Now, both of these paths converge to the same destination. It's just a matter of how they reach that destination, and that destination being the autonomous reality of eVTOLs. The piloted path starts with the eVTOL having manual control, right? They control it manually, and then over time they rescind that control and let the eVTOL fly on its own. Then you have the pilotless path, where from the get-go, from the beginning, there is no manual control. Instead, they have autonomous testing, but they start with controlled environments to more complex and erratic environments, right? Up until the very end, where they can confidently say that the eVTOL is fully autonomous. It's also important to note that these technologies are still being researched and developed. None of the technologies that I'm going to talk about in this video are the end-all be-all, written in stone methods and technologies in the advanced air mobility space. They're all being tested as we speak. I must make it clear before I go into the deep dive of these technologies that I'm not an expert. I'm a student. I'm learning. I want to expose myself to these technologies and learn more from here on out. This is a great starting point for anybody interested in just learning, and I'm here to take my research and make it more digestible for you guys, to make it more interesting, to make it more engaging, and to see really what it's all about. So there's 4 main categories in autonomous technology for eVTOLs. There's automated control, there's decision making, there's flight and perception, and then there's safety and reliability. Now here, the image in front of you is kind of a visual diagram of how the vehicle architecture works. You start at the perceiving and sensing of things. How does the eVTOL see it, right? And then you go into decision making. What do I make of that information? What do I do? What should I tell the eVTOL to do, right? And then it goes to control, right? How is the eVTOL going to act with the actuators? How is it going to control the throttle, the position of the eVTOL in a smooth manner so that it doesn't warrant turbulence and irregularities and vibrations, right? So all of these work in tandem within the realm of safety and reliability, because that is the most important here. If it's not safe, if it's not reliable, even if these technologies work, there is no vision for them to be commercialized. So all of these must be met, and we'll cover all of these 4 topics one by one and really dive into the potential technologies that are being used here at the cutting edge of these categories. Okay, let's talk about sensing and perceiving. How will eVTOLs sense things, and how can they make up of what it is they're actually sensing? Sensing is seeing, perceiving is understanding. And in the realm of eVTOLs, sensing is much easier than perceiving. It's very complicated to make a machine try and understand what it is they're looking at, right? Versus just sensing it purely through something like an IMU, for example. Let's dive into sensing first and then go into perceiving, perception. That's a massive idea here. Now let's talk about sensors. How do eVTOLs see things? For eVTOLs in particular, they sense using either IMUs, GPS, or range sensors. Now GPS, what is that? I'm sure we've all heard of it, and in fact 99% of us probably use of it on a daily basis. But how GPS actually work, and they stand for Global Positioning System, is by sending a signal to a satellite and having them return that signal, and the time it takes for that signal to reach can give us the exact location of an object. Now GPS can be very useful, but in the application of urban air mobility, especially in dense urban areas, a lot of the times those GPS signals can be blocked due to the many obstructions that may lay in the way. Then you have something called an IMU, which stands for the Inertial Measurement Unit. And essentially what an IMU does is take positional and rotational data of the actual vehicle. So we have accelerometers, gyroscopes. Accelerometers being able to measure how fast an object is accelerating, which can give you how fast it's going in speed, right? And you can have a gyroscope which can measure the actual orientation of the object, right? For example, the MPU 6050, that's a module that is applied in many electronics. And in drone builds, for example, just basic drone builds, the one you see handheld everywhere, they use IMUs so that the drone knows at what orientation it's at. Now, these IMUs can be quite problematic for eVTOLs in particular. More specifically, the presence of propagation bias and integration drift. And basically what those two terms mean is that for propagation bias, there's a small chance an error can be inputted as data. You know, maybe even though the drone is slightly turned, it can give an error where it's actually straight up right. Those little errors can happen. And because of those errors, it can lead to integration drift, which is essentially the accumulation of errors, right? So if at one point it thinks the drone is here, even though it's straight up, right? Then once it's actually straight up, it's actually going to be a bit turned even in that position, and it kind of builds up exponentially. So IMUs can be quite problematic here, but there are workarounds. Then you have range sensors. I mean, these sensors are like those ultrasonic sensors, those radar sensors, those LiDAR sensors. And essentially what all these sensors do is determine the distance of something from the signal that they transmit and receive. Now, civil aircrafts use something called the ADS-B systems. And essentially what these systems do is send GPS data to air traffic control centers for smooth and seamless flight. However, these ADS-B systems are currently too large for eVTOLs. eVTOLs right now has to find an alternative for its range sensor capabilities. Now let's talk about perceiving. Now, perceiving is a whole other ballgame when it comes to eVTOLs, so much so that we can't even really give concrete methods for how eVTOLs should perceive things. Instead, how we're going to approach perception here is by taking 3 separate challenges where perception can happen and then list potential technologies that can help mediate or completely solve and control that challenging environment. And those 3 specific challenging scenarios that eVTOLs need to learn how to perceive in is in air target detection, in landing during failure, and in satellite denied environments. Let's talk about air target detection. In order for eVTOLs to fly seamlessly and cooperatively with other eVTOLs, they need to at least be able to understand who in the air is air targets versus actual obstacles. And one way this can be done is by using electro-optical sensors. Now, these electro-optical systems can be summarized in the following diagram in front of you. It starts off with the actual sensors, and those sensors send those waves through a set of optics, and those optics redirect those waves to specifically the detectors. And the detectors here is what makes this whole system unique. Those detectors take those signals of light, of waves, and turn them into electricity. And when I say electricity, I mean electrons, more specifically. There's many detectors out there. For example, the charge coupled device, also known as a CCD, takes in what I just mentioned, that light into electrons. And there's other detectors out there for specific applications. You have the infrared sensors, right? Infrared detectors, where you could take in infrared data and turn it into useful information. So there's a variety of detectors out there, and really the possibilities are very, very vast. And then once you have this useful data, right now in the form of electrons, it's sent to the processing unit. And this processing unit turns this information into images, into visualizations, into things that we can interpret and ensure that what the eVTOL is seeing is what we are also seeing. Now, these interpretations that are being processed can further be refined through algorithms and image enhancement and target recognitions so that whatever we're seeing is more accurate, and the eVTOL can actually have a greater perception through the object that they're sensing. And lastly, this actual image can be then displayed to the cockpit for whatever reason, maybe it in testing or for the passengers to see exactly what is in front of them. Now, one of the main downfalls of this technology is that research has shown that it's at its upper limit performance due to the complex environments of eVTOLs, meaning that there's not much research and development in this specific department here. Then we have millimeter wave radars, and these work similarly to how bats locate themselves. Bats are blind, and they only locate through their sound waves, through something called echolocation. And these millimeter wave radars work in the same way. To further dive into how these millimeter wave radars actually work, you can actually increase the accuracy of the sensors using something called a frequency modulated continuous wave. Now, FMCW actually works by continuously changing the frequency of the waves. And as you can see on screen, if you're continuously changing the frequency of the wave, you get a chirping effect, assuming that a higher frequency is a higher pitch and a lower frequency is a lower pitch. And the frequency, like you've seen earlier, is the distance between the peaks of those waves. Now, without getting too technical, being able to change these frequencies give back more accurate data. And the reason this happens is because when the signal is being sent out, depending on if the hit object is moving forward, backward, or wherever, it will return at a certain time delay. All right. If you've heard of the Doppler effect, this is also in play, right? However, if you're able to modulate those signals, if you're able to continuously change those frequencies, then you could really see a precise change of those time delays. And the more precise you could see those time delays are, the more accurately you can determine what it is you're looking at. Is it moving fast? What is the potential or estimated movement of the actual object in front of you. And millimeter wave radars are great because they're immune, well, not completely immune, but they're strong against particles. And when I say particles, I mean walls and structures, right? They're strong and they can move through all of those, but it's not perfect, and there's still a ways to go to improve these millimeter wave radars so that they can work in a variety of complex environments. Okay, now let's talk about landing without failure. It's imperative to understand that these eVTOLs need to land even in the case of emergency, especially if they're autonomous. Now, one method you could use is image classification and segmentation, and this works because it can identify when the eVTOL is in a state of failure and work accordingly, because this technology is independent of vehicle mechanics. Now, within image classification and segmentation, you have technologies such as the HOG and the SVM. Now, the HOG, also known as the histogram of orientation gradients, takes an image, splits it up into cells, and in each cell they could see all of the edges that exist and at what direction it's pointing to. And this information of edges at each cell is converted to a graph, right? Like a bar graph. You could see what is most prominent at what orientation, where is the line facing in each cell, and what's most prominent and what's least prominent. You can see in the image here, it really illustrates this idea very clearly. Then you have the SVM, also known as a linear support vector machine, and it works directly with the HOG to classify what an image actually is. So it takes that data that the HOG got and it separates two certain categories, let's say cats versus dogs, and they plot those characteristics of each category on a graph, right? As you could see in the image here, you have the left side, let's call those orange blobs cats, and those are properties of a cat, and those properties can be organized in a way of a graph, for example. And then on the other side, in the bottom right, you have dogs, and it should look like this, right? It should be separate. These two classifications, these two parameters that define these two categories should be such that they are separated easily in the bar form. Now in the middle, what you see there is the hyperplane. It's a line, as you could see, but in reality it's a plane. And this plane basically is the location at which on both sides of that plane, that is the shortest distance between those 2 points. Right? And the SVM's job is to find this hyperplane, and this hyperplane is useful because it defines the intersect or the difference between these two objects that can be misinterpreted as the same, right? These computers need to understand what is what, and how to differentiate from each other. And that hyperplane basically gives those eVTOLs a defined way of saying, hey, you know what? Okay, that's a cat and that's a dog. Another technology under image classification and segmentation is edge detectors. And as the name suggests, it can detect edges. So you can see from the screen in front of you, they have a high brightness on where the edges exist and a low brightness elsewhere. This way, the eVTOLs can identify and detect where the edges are and classify those as boundaries that they might not want to fly towards, for example. Then you have semantic segmentation, and this can be combined with safety evaluation. And how it works is it can divide a picture up into different parts, and wherever the area is that is suitable for landing, the eVTOL will approach. And you can take the image here where it can identify what exactly is the background, which parts exactly is the animal. This is a simplified version of it, but in the application of eVTOLs, it would look down in a bird's eye view, identify where it needs to land, and perceive the landing site for what it is. Okay, now let's move on from image classification and segmentation. We have a technology here called 3D point cloud. And this technology allows us to identify an object in full 3D. 3D point cloud technologies can represent an object in 3 dimensionals by defining certain coordinates, and those coordinates could be a pixel of the object, for example. Now this can be achieved through something called a multi-frame monocular camera motion estimation. This is basically a single lens camera that captures the essence of an entire object by moving the camera all around and capturing every single coordinate of that object. The camera takes multiple pictures from a variety of perspectives and ties it all together using the 3D point cloud technology, creating an image like you see in front of you. Then we can build on this technology towards something called binocular parallel maps. Now this is a different kind of technology, but the essence is somewhat the same. Instead here it uses multiple cameras and it kind of captures the depth of an object, which is why we have two eyes. And they find something called a parallax, and that parallax defines or suggests the depth of a scene. Alright, we've already covered the air target detection and the landing without failure. Now let's go into the technologies, talking about how these eVTOLs can access and function in satellite-denied environments. Now when I say satellite-denied environments, I'm talking about spoofing attacks. I'm talking about intermittent signal failure, especially in dense urban areas, right? So what technologies can combat these, especially in the realm, and more specifically in the realm of perception? Now, one possible solution to this issue is something called the VIO, also known as the Visual Inertial Positioning Odometry. And the VIO exists on the eVTOL to give information on what is around the eVTOL, what is the eVTOL doing. And it consists of two main parts, the VIO. You have the visual part and you have the inertial part. The visual part captures the images around the eVTOL. This could be bird's eye view on the bottom, could be in front, really could be anywhere. But the idea here is to capture the movement of the vehicle. By capturing multiple pictures in an instance, if it's flying, then based on the change of those pictures, it can know how fast it is moving. Then you have the inertial aspect of the VIO, and it's similar to the IMU. In fact, it is an IMU sensor, and it collects data on where the vehicle is at, how fast it's moving, what is its orientation, etc. Now, if you combine the visual and the inertial aspects of the VIO, you can actually achieve something called SLAM. And some of you may have heard of this before. It is a familiar term if you are in the area of autonomous technology. But essentially SLAM, also known as simultaneous simulation and mapping, creates a scene of what is actually happening around the vehicle in real time. And it consists also with a comparison algorithm that compares the simulation and what's actually happening in real time. And it finds the discrepancies between the two, and it makes more accurate decisions on what reality is. However, there are some caveats to this technology. The VIO in particular is prone to errors. Even if one image is off by a little, when I'm talking about the virtual aspect of the VIO, even if one image is off, the preceding images will also be off in that same amount, and it'll actually snowball into an accumulation of errors. Now, fortunately though, there is still lots of room to improve, and right now there's ongoing research to increase this accuracy by a considerable amount, and to decrease the presence of these errors. And more specifically, there's research going on in the realm of closed loop detection. I'm not going to go too in depth into what that is, but if you're interested, there's a link down in the description. Additionally, you can also use something called semantic maps. And in the application of semantic maps, you would have some sort of camera or visual capture, typically in the bottom of the eVTOL that sees the ground in bird's eye view, and it can identify certain objects in real time. It creates a map. Like in the image shown in front of you, it can identify stop signs, roads, specific objects, and the eVTOL can make judgments and make decisions based on this perceived information. Now that we've covered how eVTOLs can perceive and sense objects, let's dive deep into the decision-making process. How will these eVTOLs decide what it needs to do based on the input sensor and perception data that we've just previously discussed? Now, if you want to talk about the decision making here, there's two main areas. You have rule-based and then you have data-driven. Now, what do I mean when I say rule-based decision-making technologies as opposed to data-driven? Mind you, these rule-based technologies do use data, but it's about how they make the decisions, right? What governs the decision-making process? And it's based on these rules. Multiple technologies use these rule-based methods that I'll be covering. One of those technologies is called fuzzy logic. Now, what exactly is fuzzy logic? We as humans, oftentimes when we make decisions, we have to consider a plethora of factors that sometimes we ourselves are not even conscious of. So, and oftentimes in algorithms, especially when you're trying to make basic decisions, coders may know that you use if-then statements, basic if-then statements. If this is true, then do that. However, like I've said, oftentimes in the real world, when you're making these complicated decisions, it's not as simple as doing something because of this setup or this reason, right? So fuzzy logic essentially emulates our idea of common sense when making decisions in math, in algorithms. Now, how does it do that? In fuzzy logic, they turn inputs that are usually booleans and convert them to a range of values. This range of values will then be able to be implemented into a rule base. So this is essentially what fuzzy logic is doing, right? It converts what is usually boolean inputs into those range of values. And this whole act of turning boolean values into a range of values, oftentimes in percentages and in many other forms, this is the act of fuzzification in fuzzy logic. Now, once the data values are fuzzified, they are implemented into a rule base. And a rule base basically governs the entire decision-making process. So, for instance, you could have, if it is 20% cold and velocity is 80%, then decrease in altitude or increase in altitude, whatever it may be, right? And a specific rule base is defined within a decision-making system, and depending on the input values that come in, an output is generated there. Now, mind you, in this rule-based set, when an output is created, that output is still fuzzified. It's still in a state where it might not be useful for certain algorithms, right? And it has to go through another process called defuzzification. And that defuzzification allows what used to be sort of this range of values that is sort of vague for a way to describe it, and it converts it into a distinct statement that can be easily used in an algorithm that can further actuate certain mechanisms. So that's fuzzy logic. You're essentially able to make decisions based on a rule set, right? Turning what was Boolean and distinct inputs into fuzzy inputs, putting it into a rule base, turning them into fuzzy outputs, then defuzzifying them into stable outputs used for an algorithm. Now, another rule-based decision-making technology is CEP, also known as complex event processing. And complex event processing works by analyzing a live stream of data. You could imagine like a server that's running at all times, and you see constant lines of code or text that continuously update the system on what is going on continuously at every second. And CEP takes this stream of data, right, and recognizes the patterns in this ever-flowing continuous data. And based on those patterns and things it recognizes, it can make certain decisions, right? Maybe they notice a pattern that's about to come, and hey, based on that pattern, I think this is what the best course of action is. CEP and fuzzy logic are two rule-based technologies that are used in the decision-making scope of autonomous eVTOLs. Now that we've covered rule-based technologies, let's dive into the data-driven decision-making technologies. Now, let's just cover one technology here, and it's called the mission planning method. So the mission planning method works by taking in data from a variety of sources like GPS data, GIS data, map geographical information, sensor data, and much more. And it uses this data in its entire method that works hierarchically to allow the eVTOL to make decisions in real time. Now, the mission planning method works within three main areas. You have the mission planner, the behavioral planner, and you have the local planner. I have to say that this works hierarchically, meaning that the mission planner here is on top, followed by the behavior planner and the local planner. And this hierarchy works because the local planner at the bottom depends on the behavioral one, which also then depends on the mission planner. So let's describe each of these three hierarchies one by one. You have the mission planner. The mission planner essentially finds the most optimal route through GPS data and other means. So based on where the eVTOL needs to go from a certain point, the mission planner finds the best possible route. And while this mission planner is doing this, you have to understand that there's a lot of information that comes into play, such as the geographical zone the eVTOL is in and its USSP, the service provider, which gives information on the other routes of the eVTOLs. This is basically the most important of the entire mission planning method. However, this cannot work alone. The mission planner needs help from the behavioral planner. Now, the behavioral planner works by giving a set of instructions in a variety of contextual scenarios. And these scenarios vary in many forms, such as, is it at a certain altitude? Is it at a certain density? Is it at a certain speed? Is the vehicle acting in a certain way that requires more attention? And the behavioral planner takes all of this into account and understands at what context the eVTOL is actually existing in. And if so, what are the set of instructions that the eVTOL needs to execute to fly continuously, right? So this is the behavioral planner. And then it moves even lower than that. And this is more minute and more intricate. The local planner gives a set of instructions for specific and precise movements, right? Now, these specific and precise movements could be, is it really close to a wall, right? If it's really close to a wall, let's exactly, based on the distance, based on the angle, tilt the rotor a specific way, angle the entire eVTOL a specific way. These are minute and precise and exact instructions that the local planner needs to calculate and execute for all of this to work. Now, all of this in conjunction gives a pretty robust decision-making system that is driven by data. Now, let's take this idea of the local planner and connect that to the next overarching topic, which is autonomous control. Let's talk about automated flight control. We've talked about how the eVTOL can sense and detect things, make sense of that through decision making. But now let's think about how is the eVTOL going to interact with its actuators in real time to ensure stable flight, all of which is going to be autonomous, right? So control, what exactly is it? The key word here is control, right? Think about when you're driving a car in a bumpy road, the suspension system allows the vehicle to still traverse in a relatively smooth motion, right? This is essentially what control is. We want to make sure that the eVTOL can fly straight, even amidst extreme conditions, and that the eVTOL can descend and accelerate and do whatever it needs to do, all its functions, without it going haywire, right? You need to have control. So there's a variety of control methods here. Namely, you have linear, you have non-linear, you have intelligent, and then you have integrated. So we'll cover each of these methods into detail and some examples maybe along the way to help consolidate the understanding of these technologies. So let's talk about linear control methods. When we talk about linear control methods, it's essentially taking an input value and then determining an output value. So let's say, for example, if I am moving at X speed, then the throttles need to be kept at Y throttle, for example, right? It's a simple in and out function. And one of the most popular linear control methods out there is called the PID controller. So PID works in three sections here, three areas. You have P for proportional, I for integral, and D for derivative. So how does this controller work? The proportional function starts by outputting a certain error based on its input. So let's say the intended altitude for the eVTOL is 30 feet, for example. If the input reads that it is at an altitude of 20 feet, the proportional will output an error of 10 feet, since the difference between 30 feet, its intended position, and its current at 20 feet is 10. So the proportional portion of the PID will output that error. Technically, you could stop here if you have a machine that says, okay, let's gauge where we want to be, gauge our current position, and then change accordingly to maintain that. Then that's the control. That's the entire controller. That's what you'd think, but in reality, that's not the case. What would happen oftentimes is that the proportional part of the machine, ironically enough, can make an error. So let's say the input sensor is a bit off. It might read 20 feet in real time, but in actuality, it's maybe at 22 feet. The proportional part will then give an error back of 10 feet. But since in real time that is too much, the proportional will give an error that exceeds, right? It would actually put the eVTOL at the location of 32 feet rather than 30, since discrepancies exist, right? So how do we account for these errors? That's where the integral and the derivative portion of the controllers come in. The integral portion of the PID controller essentially looks at all of the past accumulating errors and generates a more robust, a more informed output. So let's say the integral part of the PID notices that the proportional part has been off consistently with 3 or maybe 6 feet. The integral portion will consider that and fix the output inside of the PID controller. And then you have the derivative portion of the PID controller, which extrapolates the future errors, right? If taking the understanding of what a derivative is, taking the slope of an entire continuous function at a certain point, right? And then determining, extrapolating what the error could be in the future, that's what the derivative portion does. It essentially guesses what errors could happen and then accounts for those errors in real time as it's giving out an output based on the input. So essentially in the PID controller, you could imagine the PID controller as a block. It takes in an input and gives an output that fixes it. And the PID controller is essentially just math combined with these input values. It's a set of equations that are working in tandem to create the desired output. So these are PID controllers, and they're very fascinating, and they're used in a variety of applications, not just in eVTOLs, but in many other industries. So this is the more comprehensive understanding of what a controller could be like, and it's a great starting point if anybody's interested in diving deeper into this type of technology. And then you also have LQR controllers, which is also linear, but instead of taking in raw input data and turning it into outputs, the LQR, which is the linear quadratic regulator, is based on a well-defined system. Linear controllers, there's a variety of them. You can't really cover them all. Let's move on to non-linear controllers. So what makes it non-linear? Well, there are certain environments and circumstances where one input can't be correlated to one output. For example, when you're looking at biomechanical systems, let's say position of your hand is at a certain point, but the output you need is a movement of your shoulder. You can't just say the movement of your wrist is directly correlated to the output of how much you move your shoulder. This wrist, it depends on the elbow, which then depends on the shoulder, right? There's a lot of things to consider, and nonlinear controllers seek to give control outputs when the inputs are complicated and complex, such as the one I've just described. So an example of a nonlinear controller is backstepping controllers. So the backstepping controller takes the variables that are least dependent and builds up on those variables that are dependent on the former variables. And this all works in conjunction just to give out that one output that the controller seeks to give. And a bunch of the other nonlinear control methods follow this exact same idea, where it decomposes a complex nonlinear system into digestible, smaller chunks. Now let's talk about intelligent control methods. And these intelligent control methods are inspired by the modern technologies that are just making its mark today and recent years with the emergence of artificial intelligence. And the control methods that we're going to be talking about here can be split into two areas, where you have your reinforcement learning type of control and you have your deep learning control. But how do they actually work? So let's talk about reinforcement learning. So how does reinforcement learning work? Well, it works through a trial and error process. It takes a bunch of runs, a bunch of tests over and over and over again until it finds an optimal solution. And as you can see on screen, this is a video from a game called Trackmania, where someone was able to use reinforcement learning to make a car beat the best players in this game. So this is a game I love to watch, and it's just a racing game where it becomes pretty competitive. To see somebody make a reinforcement learning model and apply it to this game, and not only see it work but succeed, beating the world's best players, it really sets the tone and gives an idea of what reinforcement learning can actually achieve. Now, how these reinforcement learning technologies work is through something called a Markov decision process. And these Markov decision processes just work by giving an action based on an observation. And it does this through policies. So based on one test, for example, in the reinforcement learning environment, as soon as it sees one test, the Markov decision process just observes a simple thing, what is it doing, and tells it to do something. It's simple if-then statement. So if you want to look more into it, the reinforcement learning model uses these technologies to really give a robust and a high-performing output in these control scenarios. Then we have deep learning. And deep learning works by taking a data set, an input, such as from a sensor, for example, and parses it through its deep learning circuit and system to give an output based on probability. So how these deep learning technologies work is by using something called a neural network. And as you can see on screen right now, this is an example of a neural network. And those columns of circles that are in the middle, not the first or the last, those are the hidden layers. You can imagine each column as a layer. And the starting point is from the left and the end point is on the right. And all this deep learning technology does is that it takes an arbitrary input and it makes an understanding of what that input is trying to entail through hidden layers. And there's a bunch of advantages and disadvantages for how many hidden layers you could have. For example, the more hidden layers you have may give a higher confidence of the output that it is observing and wants to enact, but at the price of computational power and time, right? So engineers need to decide the optimal amount of hidden layers based on the given data set that they have to ultimately yield the output that they are seeking. And what's really interesting about this deep learning technology is that it can really excel in unpredictable and complex environments. And just recently, Geoffrey Hinton from the University of Toronto actually won a Nobel Prize for its contribution in neural networks. And lastly, we have integrated control. Now, integrated control just takes some of the past control methods we've talked about, namely linear, nonlinear, intelligent, combines them and makes the most use for them in a robust way. An example of this integrated control technology is the MMAC, which is short for the Multiple Model Adaptive Control. All the MMAC does is that it decides when the optimal time is to use a specific control method. For example, in a calm scenario, in a calm environment, it may opt to choose a linear control method since it saves on computational time and power. Whereas if it was in a more complex environment, it may opt to choose intelligent or nonlinear control methods. Lastly, let's talk about the safety and reliability of autonomous eVTOL technology. Let's talk about how the industry is actually developing some methods to ensure that our autonomous eVTOL technologies are safe and reliable. So one of the technologies under safety and reliability is called hardware in the loop. And hardware in the loop essentially mimics what the prototype eVTOL would behave through code and simulations and logic. Essentially, what a hardware in the loop model might look like is it has a bunch of electric control units, each control unit fulfilling its own specific purpose. For example, you may have a brake control module, and that module governs the function of how the vehicle brakes. You could have another module that governs how the doors open and close, another specifically for the traction power module, for example, another one for the suspension, and all of these ECUs work in tandem to function the vehicle. And this is a common architecture in electric vehicles. So our existing knowledge of hardware in the loop for electric vehicles can be translated to eVTOLs. And as a matter of fact, NASA and the Federal Aviation Administration have already developed hardware in the loop models for rotorcraft vehicles. So we already have a basis to work with. And as you can see on the screen here, it looks complicated, but all those blocks that you see are just logic, right? if this happens, do that. And you'll have mathematical operations in there as well, for certain things. And it's, a bunch of gates and switches in there, common logic, and it just all is organized in a way such that an input value can warrant output values in the entire electric vehicle system. So it's very interesting to see how it all works. It essentially allows engineers to guess how the eVTOL would react in specific scenarios. And I shouldn't say guess, they are engineering it and estimating it with pretty clear and concise data in this hardware-in-the-loop technology. Now, alternatively, you can manually test flights inside of the eVTOL's flight envelope, right? Making sure that it functions well in its intended environments. You also have automated test flights where you could actually see and observe and document how the eVTOLs fly and certain things they need to be worked on, and these eVTOLs won't be able to be commercialized until it meets a certain set of standards, unless it's approved by international bodies like the FAA, like ICAO, for example, like the EASA. Now, there's a strong emphasis on fault-tolerant technology in developing these eVTOLs, and fault-tolerant technology essentially ensures that in the event of a failure, in the event a component doesn't behave how it's intended, the eVTOL will still be able to function. And it should be able to detect that something's wrong and still function up to the point where it can be fixed. And in the realm of these fault-tolerant technologies, you have the redundancy aspect of it. You have hardware redundancy, and then you have analytical redundancy. And redundancy just essentially means that there's an extra part. There's an extra duplicate backup that ensures that if one fails, it can still function. In hardware redundancy, you can imagine if one component of the entire mechanism fails, it can function. For example, you have those dual brake motors. If the rear brakes fail, the front brakes can still work because that's how the system is designed. The difference between a series circuit and a parallel circuit is an example of a hardware redundant design, where if one part of that circuit fails, the two other junctions of the circuit can still parse through current. So this is the idea of hardware redundancy, and it's implemented in a lot of these eVTOLs to ensure that safety is shown and exhibited. Now, analytical redundancy, on the other hand, works by having duplicate algorithms. You may have an algorithm that constantly checks for the position of the vehicle per se, but you might have another algorithm that does the exact same thing. And those two exist, even though they're doing the same thing, those two both have to exist because they have this analytical redundancy. If one fails, the algorithm can still function. And additionally, these algorithms that are made for analytical redundancy, they can compare the data for each other. And even in the case where they are both working like they should be, they can help each other and create more effective and confident outputs. Okay, but what else do we have to know in the case where these systems actually fail? Now, these fault-tolerant technologies can respond either actively or passively. Now, when the fault-tolerant technology responds passively, it doesn't actually fix the issue that's happening. Rather, it acknowledges that the issue presented itself and knows it's there, and not only that, but it logs real-time data when the issue is happening. So the next time when the eVTOL is stationed, an engineer can look into the logs, into the data, and see exactly what went wrong and fix accordingly. Not only can it stop the failure at that time, but it can also help all the future failures that could have happened in that same fashion. And then when you have active fault-tolerant responses, those technologies literally fix the issues when it happens, right? Mechanisms activate itself and behave in a way where it fixes the issue at hand. And these technologies are really needed in critical areas, usually like their propulsion systems, where if those fail, obviously the eVTOL can cease to fly. So in those cases, you would need these active fault-tolerant technologies where it can actually fix it in the event of a failure. And on the topic of understanding these technologies, the fault-tolerant technologies can also diagnose issues at hand, and they're either model-based or data-based. And these model-based fault-tolerant technologies essentially use a mathematical model and compare it with observations in real time from the sensors. And if they match or not, the fault-tolerant technology can actually understand that, hey, this issue is present, which then calls for those passive or active responses in the technology. And then you have data-based fault-tolerant diagnosis methods. And these methods can actually identify what the issue is by taking in raw data, applying mathematical operations on it, and extracting useful information from it. And an example of this technology is called signal processing. These signal processing technologies can actually identify anomalies, extract certain patterns, and essentially create more useful information for the engineers to extrapolate and design with in mind. Now, if you enjoyed this video and how it explained the overview of autonomous eVTOL technology, please don't hesitate to reach out to me if you have any further questions. I hope I sparked some interest in this topic and inspire more people to get into this industry.